Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems from the question paper CSIR National Eligibility Test held in the month of March 2025. This is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section Linear Algebra, and it is related to the concepts and the results related to characteristic polynomials and minimal polynomials. This question is placed in part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. The question ID is 706553. Further, this question is suitable for all these examinations. Right. The given question is, let T be a C linear transformation from C square to C square, where C is the field of complex numbers. For any ordered basis B of C square, let bracket T suffix B denotes the matrix of T with respect to the basis B. Suppose that B1 and B2 are two ordered bases of C square such that the matrix of T with respect to B1 is an upper triangular matrix, and the matrix of T with respect to B2 is the square of the matrix of T with respect to B1. Which of the following statements are false? We have to find out the false statements. We are given four options. Option 1, the characteristic polynomial of T can be x square plus x plus 1. Option 2, the characteristic polynomial of T can be x into x minus 1. Option 3, the minimal polynomial of T can be x square. Option 4, the characteristic polynomial of T can be x into x minus e power 2 pi I by 3. X minus e power 2 pi I by 3 in brackets. Let's now discuss the solution of the problem in detail. We have a C linear transformation T from C square to C square, and bracket T suffix B denotes the matrix of T with respect to any ordered basis B of C square. We have two ordered bases B1 and B2 of C square such that the matrix of T with respect to B1 is an upper triangular matrix, and the matrix of T with respect to B2 is the square of the matrix of T with respect to B1. It is known that matrix of T with respect to B1 is similar to the matrix of T with respect to B2. Why? Because B1 and B2 are two ordered bases of C square, and bracket T B1 and bracket T B2 are the matrices with respect to B1 and B2, and it is known for the same linear transformation T. This is the same matrices with respect to two different bases. So it is known the matrix of T with respect to B1 is similar to the matrix of T with respect to B2. That is, the matrix of T with respect to B1 is similar to the matrix of T B1 square, the square of the matrix of T with respect to B1. Let the matrix of T with respect to B1 be capital A, and T is C square to C square. So the matrix will be a 2 by 2 matrix whose first row is AB, second row is 0C, because it is an upper triangular matrix. It is given to be an upper triangular, therefore it is like this, where A, B, C are complex numbers. Agreed. Then bracket T with respect to B1 is similar to the square of the bracket T with respect to B1. That is, A is similar to A square. When A is AB0C, A square is A square, AB plus BC first row, 0C square the second row. So A is similar to this type of A square, where AC are the eigenvalues. Yes. You see capital A, what are AC are the eigenvalues. So it is an upper triangular matrix. What are the eigenvalues of an upper triangular matrix? The elements that are present on the main diagonal are themselves the eigenvalues. Therefore, A and C are the eigenvalues of A, and A square is also an upper triangular. Therefore, A square and C square are the eigenvalues of A square. So what can be the eigenvalues of AC? What are the possibilities for A and C? They will have the same characteristic equation. Why? Because A is similar to A square. Therefore, they will have the same characteristic equation. Therefore, the set of eigenvalues of A must be equal to the set of eigenvalues of A square. That means the set consisting of A comma C is equal to the set consisting of A square comma C square. They are equal set wise. Right. This implies either A is equal to A square comma C is equal to C square, or A is equal to A is equal to C square and C is equal to A square. So these are the two possibilities. So case 1, let A is equal to A square, C is equal to C square. Solving them, we get A comma C is equal to 0 comma 0 or 0 comma 1 or 1 comma 0 or 1 comma 1. It's very easy to get these values. Case 2, let A is equal to C square, C is equal to A square. A is equal to C square, C is A square, therefore A is equal to A square square. That is A power 4. That is A into A cube minus 1 is equal to 0. And A is 0 and A can also be 1. So if A is 0 or A is 1, then it is covered in case 1 already. Right? So the other solutions of A from here are real solutions have gone. So they are the complex cube roots of unity. That is A is equal to e to the power of 2 pi by 3. It is omega. And A is equal to 4 pi by 3. That is omega square. Or sometimes we write omega bar. Yes. So A comma C ordered pair can be W comma omega square or omega square comma omega. We continue in the next slide. Right. What are the possible eigenvalues of T? the possible eigenvalues of C in case 1, these are the 4. In case 2, these are the 2. Right. And we call on option 1. The characteristic polynomial of T can be x square plus x plus 1. Can it be? Can it be? So, we have seen from the above, in case 2, omega comma omega square can be the eigenvalues of T. These are all can be the eigenvalues. So, omega square can be the eigenvalues of T. See case 2. So, then the characteristic polynomial of T can be x minus omega into x minus omega square. Multiply, you will get x square minus in brackets omega plus omega square multiplied by x plus omega into omega square omega cube. Now recall the properties of the cube roots of unity. They are 1 plus 1 omega plus omega square is equal to 0. Therefore, omega plus omega square is minus 1. And omega cube is 1. Substituting, we will get the characteristic polynomial of T can be x square plus x plus 1. Thus, the option 1 is true. It is true. Option 1 is true. Right, we move on to option 2. The characteristic polynomial of T can be x into x minus 1. That means the eigenvalues can be 0 comma 1. Yes, they are present in the case 1. Therefore, this is also true. We have seen from the above 0 comma 1 can be the eigenvalues of T. In case 1, 0 comma 1 is there. So, the characteristic polynomial of T can be x minus 0 into x minus 1. That is x into x minus 1. Yes, option 2 is also true. Right, we move on to the next slide. Right, we have already seen options 1 and 2 are true, and we have to find out those options which are false. Call on option 4. The characteristic polynomial of T can be x into x minus e power 2 pi I by 3. Assume that the characteristic polynomial of T is x into x minus omega. E power 2 pi I by 3 is x into x minus. That means the eigenvalues are 0 comma omega. Now, is the combination 0 comma omega is there in case 1 and case 2? No. No. So, the eigenvalues of T are 0 comma omega. Note that they are neither in case 1 nor in case 2. Therefore, our assumption is false. Therefore, the option 4 is false. Right. We move on to option 3. The minimal polynomial of T can be x square. Assume that the minimal polynomial of T is x square. So, this is also the characteristic polynomial. Yeah. So, that means anyway, this is sufficient for me. Assume that the minimal polynomial of T is x square. When the minimal polynomial of T is x square, that is 0 is an eigenvalue repeated twice, then A is similar to its Jordan canonical form. Right? 0 comma 0. So, the Jordan canonical form corresponding to the eigenvalue 0 will be 0, 1, 0, 0. So, A is similar to this one. Yeah, you must be familiar with this minimal polynomial and the corresponding Jordan canonical form. Then only you will understand. And if A is similar to 0, 1, 0, 0, then what will be the A square? So, it is similar to 0, 1, 0, 0 multiplied by 0, 1, 0, 0 is 0, 0, 0, 0 with 0, 0, 0 matrix. A square is similar to 0. A is similar to 0, 1, 0, 0. A square is similar to the 0 matrix. But we have A is similar to A square. Yeah, we have A is similar to A square. the matrix of T with respect to B1, that is A, is similar to the square of the matrix of T with respect to B1, that is A square. So A is similar to A square. Can A be similar to A square? No. This is a zero matrix, this is a non-zero matrix. So clearly A is not similar to A square, a contradiction to the fact that A is similar to A square. Therefore, our assumption is false. Therefore, the option 3 is false. And we have to find out those options which are false. Therefore, the answer to this question is options 3 and 4. That is the detailed discussion of the solution of the given problem from the section Linear Algebra, which is related to the concepts and the results related to characteristic polynomials and minimal polynomials. And in my opinion, this question is very good question, right? And some of you, if you are not familiar with the concepts of minimal polynomials and Jordan canonical forms, for them it may not make sense, but for those of you who are familiar with minimal polynomial and Jordan canonical forms, etc., for them it is very, very clear. Right. Brush your concepts of minimal polynomial, Jordan canonical forms, and read again. So with these few words, I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes, yes, yes. I am going to meet you all once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.